Mars is a red point in the night sky, circled by 2 small moons. That is the easy picture. The harder one is underneath it. Mars carries an uneasy shape. Its north sits several kilometers below its south. Its western side holds a volcanic rise so large it bends spacecraft orbits. Somewhere in Mars's long wavelength structure lies a directional asymmetry. The obvious explanations have not fully settled. A new hypothesis asks whether part of that signal was left by a moon that vanished. The proposed body is called Nerio. It has never been seen. If real, it may have raised a tide in young Mars and frozen a directional mark into the planet's own figure. But earning that claim means surviving Tharsis, giant impacts, mantle convection, and every older explanation already waiting. By the end of this video, you will understand what the lost moon model proposes, where it breaks, and what Mars would have to show for Nerio to become more than a conditional hypothesis. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Picture Mars from orbit. Not the photographs. The numbers. The northern half of the planet sits, on average, 5 to 8 kilometers below the southern half. Not mountain ranges separating them. Not scattered craters creating a local contrast. The entire northern hemisphere is lower than the entire southern hemisphere, as if someone tilted the planet and the terrain followed. The crust is thinner in the north. The terrain is older in the south. The 2 hemispheres preserve different geological ages, different crustal thicknesses, and different records of the earliest period of Martian history. Now that contrast, the hemispheric dichotomy in the language of Mars science, has been demanding explanation for decades. A planet does not casually split its surface into 2 unequal zones without a cause. Something large happened to Mars, or something large happened inside it, or both happened in sequence. We will spend time with each explanation before we consider the lost moon. But the hemispheric dichotomy is only one of at least 3 overlapping shape problems on this planet, and understanding what separates them is the difference between following the investigation clearly and following it badly. Before those 3 problems are named, it is worth asking how we know any of this. Mars is not a world we can walk across with measuring instruments. The elevation map of Mars comes from a laser altimeter called MOLA, which flew aboard the Mars Global Surveyor spacecraft in the late 1990s. The instrument sent laser pulses down to the surface and measured how long each pulse took to bounce back. Since light travels at a known speed, the round-trip time gives a precise elevation reading. MOLA made hundreds of millions of such measurements over more than 4 years of operation. The result is a topographic map of Mars, accurate to a few meters of elevation across the entire planet. For a world roughly 78 million kilometers away at its closest approach to Earth, that is extraordinary precision, and the gravity field comes from a different method. Scientists track the radio signals from spacecraft as the orbits of those craft change subtly under the gravitational influence of the terrain below. When a spacecraft passes over a region of slightly higher mass, the gravitational pull accelerates it slightly. When it passes over a region of lower mass, it slows. These accelerations appear as tiny Doppler shifts in the spacecraft's radio signal. By cataloging those shifts across thousands of orbits, scientists reconstruct the 3-dimensional distribution of mass inside Mars. The current gravity field model is known to very high resolution, covering features at scales of several hundred kilometers and below. So we have 2 independent lines of precision measurement telling us what Mars looks like at large scales. Topography from laser altimetry and gravity from orbital tracking. Both confirm the same picture. The planet is uneven, both at the surface and through its deep structure. Look at Tharsis. It is not a single volcano. It is an entire volcanic province, roughly 5,000 kilometers across. It rises on average about 10 kilometers above the surrounding terrain. At one end sits Olympus Mons, which reaches roughly 22 kilometers above Mars's mean surface level. making it the tallest known volcano in the solar system by a wide margin. When that much mass concentrates on one part of a planet, the whole body responds. The crust beneath bends, the gravity field shifts, the rotational balance of the entire planet changes. Tharsis is so dominant on the western side of Mars that its gravitational signature shows up clearly in the orbital tracking data of every spacecraft that has ever flown around the planet. And then there is a third problem, quieter than the other two, more specific. Scientists describe the large-scale shape of a planet using mathematical functions called spherical harmonics. The name sounds technical, but the concept is approachable. Think of trying to describe the shape of a lumpy potato mathematically. The first term captures the average size. The second captures the basic squashing from rotation, the equatorial bulge. Higher terms capture increasingly fine-grained departures from a symmetric sphere. Mars's equatorial bulge from its roughly 24.6-hour rotation is well understood, but Mars also carries significant signal in terms that describe a directional asymmetry in the equatorial plane itself. More than a general outward bulge, but an elongation pointing toward one longitude more than others. Think of the equatorial cross-section of Mars not as a perfect circle, but as a slight ellipse with a preferred long axis. A perfectly symmetric rotating planet has no such directional equatorial term. Mars has one. Scientists call this component the triaxial residual, and it is the specific thing the lost moon model aims to explain. Think of it this way. If you looked at Mars from within its equatorial plane, viewing the planet edge-on, a purely rotation-flattened planet would show a round cross-section. Mars, in this view, has a slightly elongated cross-section that points toward a particular longitude. The triaxiality captures that preferred direction and its magnitude. Rotation alone cannot produce a directional equatorial asymmetry like this. Something oriented along a specific direction has to be involved. So we have three distinct shape problems on one planet. The hemispheric dichotomy, north versus south, crustal thickness, terrain age, the Tharsis figure, a dominant volcanic load that reshapes the global gravity field and may have shifted Mars's orientation relative to its spin axis, and the triaxial residual, a directional asymmetry in the equatorial plane that persists after rotation and the dominant load are accounted for. The lost moon idea does not try to claim all three, it targets the third. That specificity is what makes it a hypothesis rather than a general appeal to Mars's complexity, and that third problem, the triaxial residual, is specific in a way that matters practically. It is not asking whether Mars is uneven in some vague general sense. It is asking about one particular coefficient in a mathematical description of the planet's gravity field. The coefficient has a measured value and a measured orientation. The Nerio model says that orientation, corrected for the polar wander history, should point toward the longitude where a synchronous moon once sat. That is a direction, not a general claim about asymmetry, a direction, and directions can be tested. If the residual direction, once the dominant contributions are subtracted and the polar wander correction is applied, falls within the range the model predicts, the hypothesis is consistent. If it points somewhere incompatible with any plausible ancient synchronous geometry, the hypothesis fails this specific test. The precision of the claim is exactly what makes the investigation worth having. Mars is not just a planet that looks uneven. Mars is a planet that carries a specific measurable number, and one hypothesis says that number is partly explained by an object that vanished 4 billion years ago. But before we ask whether a vanished moon might explain that third problem, we need to feel what 4 billion years does to a physical record. Volcanoes rose and spread mass unevenly across the first few 100 million years. Impacts arrived at different times and in different hemispheres. The planet's spin axis may have shifted by tens of degrees as large volcanic loads changed the rotational balance. The interior cooled at its own pace, changing how the crust and mantle responded to stress. Material was buried, broken, and reworked by processes that did not all operate in the same era. Think of Mars as a physical archive that has been through several fires. Some records are clear. The laser altimeter gave us elevation to the meter. The gravity tracking missions resolved the subsurface mass distribution at extraordinary precision. For a world beyond Earth, Mars is among the most precisely measured planets we have. But measurement precision at the surface does not automatically resolve how the planet organized itself in deep time. The gap between what we can measure precisely and what we can explain fully is exactly where this investigation lives. And here is a discipline that has to carry through the whole story. Shape is evidence, but shape alone is not a fingerprint. A planet's long wavelength figure records accumulated effects across its whole history. Rotation shapes it, heat flow shapes it, volcanic loading, impacts, and crustal structure all leave marks. So does the pull from any orbiting body massive and persistent enough to matter. Some of those effects overlap, some partially erase one another. Some survive only because the planet cooled fast enough to preserve them before later geology overwrote the record. That accounting has been made possible by a specific generation of spacecraft: Mars Global Surveyor, Mars Reconnaissance Orbiter, and Mars Odyssey together built up the highest resolution gravity field model we have for any planet outside Earth. Each mission added orbital passes at different inclinations and altitudes, filling in the three-dimensional picture of how mass is distributed beneath the Martian surface. The current model covers features at scales of several hundred kilometers and below, accurate to roughly 1 meter of equivalent elevation at the scales that matter for the low-degree directional terms. For comparison, that is the height of a child. The measurement itself is not the problem. What remains difficult is assigning each piece of the measured signal to its correct physical cause. So we are working with data precise enough to distinguish the directional equatorial term clearly. We know its magnitude and its orientation. The question is not whether the data shows a triaxial residual. It does. The question is whether the known physical processes account for it fully, or whether a fraction of it persists unexplained after careful accounting. That is a question about models, not about instruments. And models always carry assumptions. The assumptions about Tharsis's detailed structure, the lithospheric thickness profile, the true polar wander history, and the hemispheric dichotomy's contribution each add uncertainty to the subtraction. Better models built on better constraints would narrow that uncertainty. Until they do, the gap between measurement precision and explanatory precision is exactly where the hypothesis lives. The gravity field is also telling us something about the interior and not only the surface. When a gravitational anomaly persists at low degree, the cause is either deep inside the planet or spread over a very wide area. Tharsis is so large that it contributes to the lowest degree terms, the ones that describe the whole planet shape. Both Tharsis and a proposed fossil tide would show up in the same low-degree harmonic coefficients. They are not separated by where they appear in the data. They are separated only by modeling them with different physical processes and seeing whether the sum of the known processes matches the measurement without remainder. That is the intellectual core of the entire investigation. Now, the language of spherical harmonic terms is worth holding on to, because it is the language the fossil tide model uses to make its prediction precise. The low-degree gravity terms are among the most precisely measured quantities we have for Mars. The directional equatorial term has a specific measured magnitude and a specific measured orientation, pointing toward a particular longitude on the planet. The Lost Moon model predicts that after the known large-scale contributions are subtracted, that orientation should point in a direction consistent with where a synchronous ancient moon would have sat. That is a concrete, testable prediction, not a vague appeal to mystery, a directional claim that can be checked against a measured number. So Mars presents us with a balance problem rather than a surface mystery. Before we look for a vanished moon, we need to know how much of the shape is already explained by the things we can see. The volcanoes, the impact basins, the crustal contrast, those speak clearly. The quieter directional residual in the equatorial figure may or may not speak clearly enough. That is the question. And the two moons Mars still carries are the first place to look, because their unsettled origin is part of the same accounting. Phobos was found on the 18th of August 1877 by the American astronomer Asaph Hall, working at the U.S. Naval Observatory in Washington with a large refracting telescope. Hall had spent years being told that Mars almost certainly had no moons. The planet is smaller than Earth and sits farther from the Sun. Simple reasoning suggested that any moons would either have been long since captured, broken apart, or too small to detect with the instruments of the day. Hall decided to look more carefully anyway. He was nearly ready to give up when, in the space of 6 days, he found both Phobos and Deimos. They were smaller than anything anyone had expected to find orbiting a planet. And they still are. Phobos is roughly 26 kilometers at its widest. It orbits Mars at a distance of about 9,376 kilometers from the planet's center, which puts it only about 5,800 kilometers above the Martian surface. To give that some scale, most communication satellites orbiting Earth sit at 35,000 kilometers above the surface. Phobos is dramatically closer to its planet than any satellite you might use for navigation or broadcasting. It completes one full orbit in about 7.65 hours, which is faster than Mars itself rotates. Deimos is smaller still, about 15 kilometers across. It orbits much farther out, at roughly 23,463 kilometers from Mars's center. One circuit takes about 30 hours. Now, neither moon looks anything like Earth's moon, neither fits the mental picture of a planet accompanied by a grand natural satellite. But their smallness is not the real mystery, their origin is. We have two near-equatorial, low-inclination moons orbiting a rocky planet, and after decades of observation and modeling, we still cannot say with confidence where either one came from. That unresolved origin matters here, because any model that proposes a large ancient body orbiting Mars earlier in its history has to be consistent with whatever satellite history produced these two small survivors. The capture explanation sounds reasonable as a first guess. Phobos and Deimos are dark. Their surface spectra in broad terms resemble primitive carbon-rich asteroids. Mars sits adjacent to the asteroid belt, so the idea of captured bodies feels natural. But the orbital details immediately push back. A captured asteroid normally arrives on an inclined, elongated orbit, carrying far too much kinetic energy to settle into a stable circular path. To land in the nearly circular, nearly equatorial arrangement we see today, the incoming body has to shed a great deal of energy very precisely. Present-day Mars has too little atmosphere for aerodynamic drag to accomplish this. Gravitational encounters with other bodies can help, but building a clean pathway from a chaotic capture trajectory to the smooth near-equatorial orbit we observe is genuinely difficult to model for even one moon, let alone two. Think about what those orbital properties are telling us. Near-equatorial, low-inclination orbits are exactly what you would expect from moons that formed from material already aligned with the planet's equatorial plane. If material is thrown up by an impact on Mars or spread around the planet as a debris disk, gravity naturally flattens that material into a structure aligned with the equatorial plane. Moons forming from that disk inherit low-inclination orbits. A captured body from the asteroid belt would not naturally arrive with those properties. Capture requires a mechanism to remove the extra energy, and the equatorial alignment requires an additional mechanism to explain why the orbit is so flat. The energy problem for capture deserves a moment of concrete attention. When an asteroid falls toward Mars from the asteroid belt, it gains speed as it approaches the planet. By the time it reaches the altitude of Phobos's present orbit, it would be moving considerably faster than escape velocity, on a trajectory that would loop around Mars and fling itself back out into space. To remain in orbit, the asteroid would need to lose a very specific amount of energy at just the right moment. On Earth, an incoming body can shed energy through atmospheric drag over multiple passes, spiraling down slowly. Mars's atmosphere is roughly 100 times thinner than Earth's, and even Earth's atmosphere would not efficiently capture a body the size of Phobos in this way. Gas drag from a temporary planetary atmosphere or interactions with a pre-existing moon disk have been proposed as alternatives, but each requires conditions that add their own complications. This is why capture models are not simply dismissed, but are also not considered sufficient on their own. So the in situ impact explanation has real appeal. A large impact on Mars could throw enough material into orbit to form a transient debris disk around the planet. That disk would be naturally equatorial. Moons forming from the disk would inherit near equatorial orbits. The composition question then becomes sharper though, and the debris disk pathway for moon formation is worth understanding in a bit more detail, because it is the same class of pathway that the Nerio model would require for a larger synchronous moon. When a large body collides with Mars, some fraction of the ejected material escapes the planet entirely, some falls back to the surface relatively quickly, and some ends up in orbit with speeds and trajectories that allow it to remain. The orbiting material forms a disk that spreads out through collisions among its own particles, with inner material spiraling inward and outer material pushed outward. Over time, the disk can aggregate into one or more moons, particularly at distances where the density of material is high enough for gravitational clumping to operate faster than collisional disruption. The timescale for this process is typically thousands to millions of years, fast on geological timescales. A debris disk produced by a large early impact could have created a family of moons, of which Phobos and Deimos might be survivors or descendants, while larger moons formed earlier might have since been lost to tidal evolution. That is a plausible general framework. The question is which specific sequence of events actually occurred. If the moons formed from Martian ejecta, their chemistry and isotopic ratios should carry signatures of Martian crust and mantle material. Remote spectral observations have not settled this cleanly. Space weathering alters the surface layer. Dust from Mars and from the asteroid belt moves around the inner solar system and can contaminate readings. Spectral features can be mimicked or masked by grain size effects and by the history of radiation exposure at the surface. And there is a third family of models worth introducing because it shapes how we should think about Mars's satellite history. Phobos and Deimos may descend from a single larger parent body that was disrupted. In that scenario, one bigger object ends up producing two smaller remnants through a combination of tidal forces, impact fragmentation, or both. Research modeling work has shown that a common progenitor scenario is physically plausible for certain mass ratios and orbital configurations. This matters for our investigation because it demonstrates that larger body histories are already present in the scientific conversation about Mars's moons. The idea of a bigger former moon somewhere in Mars's past is not inherently exotic, but here is where discipline matters. A disrupted progenitor for Phobos and Deimos is not automatically Nerio. The common progenitor models typically describe a body much smaller than the synchronous primordial moon that the fossil tide hypothesis requires. The orbits involved are different, the timing is different, the expected physical outcomes are different. Two stories can share a family resemblance without being the same story. What each of these origin scenarios predicts for composition is worth noting because the MMX sample return will eventually test those predictions. If Phobos formed from Martian impact ejecta, its oxygen isotope ratios should cluster around the Mars value, which is measurably different from the values found in chondritic asteroids. If Phobos was captured from the asteroid belt, its isotope ratios should resemble outer belt material, which plots distinctly on the oxygen 3 isotope diagram used by cosmochemists. If Phobos formed from a common progenitor that was itself a captured body, the isotopic signal would resemble asteroid material. If the progenitor was of Martian origin, it would resemble Mars. The predictions differ and the test is sharp. A few grams of Phobos regolith will carry those isotopic signatures in individual mineral grains that can be measured in a laboratory with precision far beyond anything achievable remotely. That is why the sample matters, not because it identifies Nerio, but because it identifies what Phobos is, and knowing what Phobos is constrains what Mars's satellite history has been. Look at Phobos's current orbit more carefully, because it is one of the most concrete dynamical facts Mars offers. Phobos orbits inside the synchronous distance. The synchronous distance for Mars is the orbital radius where a body would complete exactly one orbit in the time it takes Mars to rotate once, about 24.6 hours. That synchronous orbit sits at roughly 20,428 kilometers from Mars's center. Phobos, at 9,376 kilometers, is well inside that boundary. Because Phobos circles the planet faster than Mars rotates, the tidal interaction between Mars and Phobos gradually drains orbital energy from the Moon and pulls it inward. We have measured that drift directly. It amounts to roughly 1.8 centimeters per year. Over human timescales, that is invisible. Over geological timescales, it is enormous. In around 30 to 50 million years, Phobos will approach the region where tidal forces become strong enough to disrupt the body or pull it down to the surface. Some models predict a ring forming first. Others suggest a more rapid structural failure. Picture what that means for the larger story. The small moon we see today is not sitting in a final stable arrangement. It is part of an active dynamical process. Moon loss is not mythology. It is celestial mechanics applied across geological time. Phobos makes this vivid because we can watch it happening right now, slowly, in the precise measurements of spacecraft tracking its orbit from mission to mission. And Deimos tells a complementary part of the story. Deimos orbits at 23,463 kilometers from Mars's center, well outside the synchronous distance. Because it orbits more slowly than Mars rotates, tidal interaction pushes it gently outward rather than pulling it inward. Deimos is drifting away from Mars, not toward it. The direction of tidal evolution depends entirely on whether a moon orbits inside or outside the synchronous distance. Phobos migrates in, Deimos drifts out. Their opposite fates from the same physical process shows how the geometry of synchrony organizes the whole satellite system. Now, there is another way the existing moons matter. They remind us that the satellite system around Mars is not a static inventory. It is a snapshot of one moment in what may have been a longer, more complicated sequence. Moons have been lost and replaced in other planetary systems throughout the solar system's history. The giant planets hold dozens of irregular moons that appear to be captured bodies, remnants of a much more dynamic early history. Even Earth may have had a second small moon early in its history, according to some models, before that companion merged with the present moon. The normalcy of complicated satellite histories is part of what makes the Nerio scenario not inherently implausible, even before we evaluate its specific predictions. Disks become moons, moons become rings, rings can spawn new moons. Larger bodies can be torn apart by tidal forces and redistributed into smaller fragments. The present arrangement of two small moons is the current chapter in what may be a much longer book. So what can we honestly take from Phobos and Deimos? First, Mars's satellite history is genuinely unresolved, even for the bodies we can see. Second, complex histories involving disruption, debris disks, and multiple phases are plausible. Third, the present moons do not prove Nerio. They do not confirm that a large synchronous moon once wrote a fossil mark into Mars's figure. What they confirm is that the satellite environment around Mars is dynamic enough that missing former bodies are not physically absurd. And before any former moon can explain Mars itself, we need to understand the mechanism by which a moon can leave a mark on a rocky planet long after the moon is gone. The word tide usually brings up an ocean shoreline. Water rises, water retreats, the moon pulls. But water is only the most visible example of a much more general physical effect. A tide is any deformation caused by a gravitational pull that is slightly stronger on one side of a body than the other. Oceans respond dramatically because they flow freely. Rock responds more quietly. But rock responds too. Earth proves this directly. The solid surface of our planet rises and falls by roughly 20 to 30 centimeters during each tidal cycle. Sensitive instruments measure this every day. The ground beneath us flexes under lunar and solar gravity even though we never feel it. That matters for this investigation because it demonstrates a principle clearly. Rocky planets are not rigid in the way a ball bearing is rigid. They deform under sustained gravitational forces. How much they deform depends on temperature, internal structure, and the time over which the force operates. And tidal forces do not only stretch material, they also heat it. The clearest example of active tidal heating in the solar system is a moon called Io, which orbits Jupiter in a slightly elliptical orbit. As Io moves through its orbit, Jupiter's gravitational pull changes strength slightly as the distance varies. Io is being squeezed and released continuously. That squeezing drives internal friction. The friction generates heat. So much heat that Io is the most volcanically active body in the solar system, despite being roughly the same size as Earth's moon. Its surface is covered with erupting volcanoes and fresh lava flows that resurface the moon continuously. Io is a vivid illustration of what sustained tidal interaction can do to a body that is too close to a large planet. But Io's case is active and ongoing. The story we are exploring for Mars involves a frozen echo of a past interaction, not an active one. Now, young planets deform more easily than old ones. Early Mars was warmer, its crust was thinner, its interior carried much more heat from the accretion of material and from the decay of radioactive elements than it does today. A gravitational distortion that would make almost no impression on present-day Mars could have made a significant impression on Mars 4 billion years ago. The rock was softer, the crust had less mechanical strength. The response to sustained forcing was correspondingly larger. Here is where the fossil tide idea starts to make physical sense. Imagine a large moon orbiting close enough to young Mars to raise a measurable solid body tide, not ocean waves, not surface flooding, a broad gravitational distortion in the bulk of the planet itself. The near side of Mars stretches slightly toward the moon. The far side stretches slightly away. This happens continuously as long as the moon is there, and if the moon occupies roughly the same direction relative to the planet's surface for long enough, the deformation has a preferred axis. The tidal pull keeps working along one longitude, one direction, one geometry, and for that axis to matter billions of years later, timing becomes everything. The distortion has to exist while Mars is still warm and responsive enough to deform meaningfully. Then the outer shell has to stiffen while some portion of that deformation is still present. If Mars relaxes fully before the lithosphere gains enough strength to preserve the pattern, the mark disappears entirely. If the planet stiffens quickly enough while the deformation is still active, part of the shape can be locked into the global figure as a fossil signal. Not a visible ridge, not a detectable bulge in any image, a low-degree, long-wavelength residual in the planet's geometry. Scientists describe this planetary response using two parameters. One is the love number, called K2. It measures how readily a planet deforms under a tidal pull. A higher K2 means a more responsive, more deformable body. A lower K2 means a stiffer, less responsive one. Present-day Mars has a K2 of roughly 0.17, measured directly by InSight seismic and geodetic data. Young Mars almost certainly had a higher K2 because its interior was hotter and the lithosphere was thinner. The second parameter is Q, the tidal quality factor. It measures how efficiently the planet converts the energy of the tidal deformation into internal heat. A lower Q means stronger dissipation. The planet loses tidal energy quickly into heat. A higher Q means the tidal energy persists in the deformation longer before being converted. Early Mars likely had a lower Q than it does now, meaning it was more actively exchanging energy with orbiting bodies. Think about why both parameters matter for the story. A higher K2 means a stronger deformation response from the young planet. A lower Q means the planet is exchanging energy with the orbiting moon more rapidly. Those two conditions together govern the speed at which the moon's orbit evolves. A soft, dissipative planet gives more tidal response and drives faster orbital evolution. The conditions that allow the largest fossil mark also push the orbital clock forward fastest. There is a specific timing window buried in this problem that is worth making concrete. Mars's lithosphere was thinnest in the Noachian period, the first few 100 million years of the planet's existence. The crust may have been only 10 to 20 kilometers thick in the earliest Noachian, thinner than the base of Earth's oceanic plates today. Under those conditions, a massive orbiting moon could have produced a significant solid body tidal deformation, perhaps on the order of tens to hundreds of meters in height at the planetary surface, not visible as a ridge, but real as a long wavelength distortion in the global figure. As the lithosphere thickened during the Noachian and into the Hesperian, that window narrowed. By the time Mars reached its present lithospheric thickness of 20 to 40 kilometers at the InSight landing site, and likely much thicker elsewhere, the planet was too rigid to preserve a new tidal signal in this way. The fossil, if it exists, had to be locked in while that early window was still open. Think about what that means for the lost moon timeline. The moon had to have been in synchronous orbit during the early Noachian, roughly 4.1 to 3.7 billion years ago. That is the period when Mars was still responding strongly to tidal forcing. It had to stay long enough for the deformation to accumulate and survive the planet's early stiffening, and the planet had to stiffen at roughly the right rate, not so slowly that the deformation relaxed before preservation, and not so quickly that the deformation never had time to build. This is a narrow window in planetary history. The fact that the model requires it is not necessarily a problem, but it does mean the idea inherits a specific chronological claim that future Mars interior models can check. Now picture all the moving parts at once. First, the moon's gravity raises a directional deformation in young Mars. Second, Mars is cooling and the outer shell is thickening. Third, the moon's orbit is shifting as tidal interaction redistributes angular momentum between the planet and the moon. Those three clocks run simultaneously. The tidal deformation has to build while Mars is still warm enough to respond. The moon's orbit has to stay in the right geometry long enough for the deformation to accumulate, and the lithosphere has to strengthen before the deformation relaxes. If those three processes do not overlap correctly, no fossil signal is preserved. That sounds demanding because it is. The fossil tide mechanism is not a free explanation. It does not attach itself cheaply to any asymmetric planet. It needs a specific set of conditions: the right moon mass, the right orbital geometry, a particular thermal window in Mars's history, and enough stiffening speed to lock the signal in place. Earth's own tidal history gives a smaller scale analogy for why timing matters. Our moon is slowly pushing Earth's rotation to slow down. Hundreds of millions of years ago, days on Earth were shorter. That energy exchange between Earth and the moon has been changing both bodies gradually over deep time. Unlike the Martian case, the signature of that interaction is not frozen but still active. The analogy shows that moons and planets exchange information continuously through tidal forces. For early Mars, the question is whether that exchange left a frozen record. But the mechanism itself is physically respectable. We already know that gravitational deformations can be preserved in solid bodies under the right conditions. Many icy satellites in the outer solar system carry tidal shapes and figure anomalies that reflect earlier orbital or thermal states from before those bodies reached their current cold and rigid configurations. Rocky planets are harder cases because their geology is more active and their internal responses more complicated. Even so, the principle is accepted in planetary science. Ancient gravitational forces can leave permanent geometric signals if the conditions for preservation are met. And there is a specific vocabulary used for these preserved shapes in planetary science. A fossil figure is a shape that was produced by forces that no longer act on the body. The moon, for instance, carries a slight elongation pointing toward Earth that is larger than tidal locking theory predicts for the present-day Moon-Earth separation. This excess elongation is thought to be a fossil figure from when the moon was much closer to Earth and the tidal forces were much stronger. The excess has not relaxed because the moon's interior is too cold and rigid to flow significantly on any relevant timescale. That lunar fossil figure is not a hypothesis. It is an observed measurement and an accepted feature of the moon's shape. The Mars fossil tide hypothesis is proposing that Mars has its own fossil figure from a different origin, but the same category of preserved shape from ancient forces. The distinction is that the moon's fossil is well established, and the Mars hypothesis is not. But the category itself is real and accepted. That is one of the reasons the Nerio model belongs in a serious conversation about Mars, rather than on the speculative fringe. So this is where we stand. We have spent time understanding why Mars is physically uneven, why its existing moons are mysterious and dynamically active, and how a moon can leave a mark in a planet's geometry after the moon itself is gone. The mechanism is possible in principle. We know it requires a narrow set of conditions: the right mass, the right orbital configuration, the right thermal timing. And we know that the mark we would be looking for is not a visible feature on the surface, but a low-degree directional signal in the long wavelength figure. The next question is whether the model proposing that signal also gives us a physically coherent ancient moon. A name can make a hypothesis easier to follow, but names also tempt us into treating proposals like discovered objects. The ancient moon in this story is called Nerio. The name comes from Roman mythology, linked to Mars as a martial deity's companion. The body itself has never been detected by any instrument in any wavelength at any time. What the model actually proposes is specific. Early Mars has a moon in synchronous orbit. Synchronous here means the moon's orbital period matches the planet's rotation period. Mars rotates in roughly 24.6 hours. A synchronous moon orbiting Mars would complete one circuit in roughly the same time. The synchronous orbital radius for Mars sits at approximately 20,428 kilometers from the planet's center. That is about 17,000 kilometers above the Martian surface. To feel that distance, compare it to the two moons Mars actually has. Phobos orbits at 9,376 kilometers from Mars's center, well inside the synchronous zone, which is why it drifts inward. Deimos orbits at 23,463 kilometers, outside the synchronous zone, which is why it drifts outward. A synchronous moon at 20,428 kilometers would sit between those two positions, roughly twice as far from Mars's surface as Phobos, but slightly closer than Deimos. And unlike either Phobos or Deimos, it would not visibly rise or set. From the surface of Mars, a synchronous moon would appear to hover nearly fixed over a particular longitude on the equator, tracing only a small arc day after day, rather than sweeping across the sky. Now that orbital geometry matters enormously for the fossil tide idea. A synchronous moon creates a persistent direction for the tidal pull on the planet below. The near-side distortion keeps pointing toward the same longitude on Mars. The tidal force does not sweep randomly around the equator as the moon goes through a rapid orbit. It works along one axis, over and over, building up a directional deformation in the young planet's figure over thousands to millions of years. In the model, that persistent pull raises a solid body tide in early Mars, while the planet is still warm and the lithosphere is still thin enough to respond. Then Mars cools, the lithosphere thickens, some portion of that directional distortion is locked into the global figure before the planet becomes stiff enough to stop responding. Later the moon's orbit becomes unstable. Solar tides, the gravitational influence of the sun on the moon's orbit, can nudge a synchronous Martian moon away from the balanced configuration. Once the moon drifts from synchrony, ordinary tidal evolution takes over, and the orbit changes more rapidly. Eventually the body is removed, broken up, or otherwise lost from the system. The moon disappears. The shape signal, if the preservation conditions were met, remains. Think about why that is scientifically attractive. The model is not simply proposing a ghost object out of thin air. It is proposing a ghost object that leaves a specific, measurable consequence, a directional residual in the low-degree gravity field of Mars. The model makes a geometric prediction about the orientation of that residual and an amplitude prediction about its magnitude. Those are the kinds of predictions that can fail cleanly if the evidence does not support them. That is what makes an idea scientifically useful. The method here has precedent in the history of science. The planet Neptune was first predicted before it was ever seen through a telescope. Two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, working independently in the 1840s, noticed that Uranus's orbit was not quite right. The planet was drifting slightly from where its orbital calculations predicted it should be. Both men reasoned that an unseen body must be pulling on Uranus gravitationally. Both calculated where that unseen body should be. When a telescope was pointed at the predicted location in September 1846, Neptune was there. The prediction worked because it was specific enough to check against the sky. The Nerio model follows the same logic at a different scale. Infer an absent object from its surviving physical consequence, and the model is narrow in a way that is both a strength and a test. Nerio does not claim to explain the hemispheric dichotomy. It does not explain Tharsis. It does not claim that Phobos and Deimos are confirmed remnants of this ancient synchronous moon. It aims at one particular directional component of the long wavelength figure that survives after the dominant known contributions are handled. A broad claim that could be attributed to almost anything would be easy to enjoy and hard to falsify. A narrow claim about one specific component of one measured quantity can fail cleanly. That is what makes this worth taking seriously. And it is worth pausing here to notice what kind of claim the Nerio model is actually making. It is not claiming that Mars looks strange, which is easy to say and explains nothing. It is not claiming that big moons can deform planets, which is true but not specific to Mars. It is claiming that a particular numerical value in the current gravity field of Mars, specifically the directional equatorial term in the low-degree harmonic expansion, has a component that points in a direction consistent with an ancient synchronous orbit after corrections for Tharsis and polar wander are applied. That is a narrow claim with a specific number attached. Every word in that sentence can be checked. The number exists in the gravity field data. The Tharsis correction can be modeled. The polar wander correction can be estimated. The orbital geometry produces a prediction. The test either passes or fails. That kind of specificity is what distinguishes a scientific hypothesis from a story. But the weaknesses are obvious and must be stated plainly. Nerio has not been observed. Its mass is inferred from the model requirements. Its orbital geometry is inferred. Its timing is inferred. Its formation pathway is inferred. Its removal mechanism is inferred. The direct literature source is a new model and preprint, not a consensus view built over decades from multiple independent lines of peer-reviewed investigation. So the idea is only as good as the distinctiveness of the signal it claims to explain, and only as good as the quality of the physical assumptions behind it. And it is worth asking what the model actually predicts about the magnitude of the residual signal, more than its direction. A moon of a given mass, orbiting at the synchronous distance during a period when Mars had a given love number and quality factor, would produce a tidal deformation of a calculable size. The fraction of that deformation preserved as a fossil signal depends on the ratio of the stiffening timescale to the relaxation timescale, both of which depend on the thermal history. The model predicts not only a direction for the C22 and S22 residual, but also a range of amplitudes consistent with physically plausible moons and early Mars interior conditions. If the observed residual amplitude is within that range, the hypothesis is consistent with the data. If the amplitude requires a moon so massive that its orbital evolution would have been far too rapid to allow the required residence time, the hypothesis struggles even if the direction is correct. So the amplitude and the direction together form a two-part test that a simple appeal to Mars is asymmetric cannot pass. Think about what planetary scientists do when they encounter situations like this more generally. They routinely infer absent causes from surviving consequences. We infer early magnetic fields in Mars from remnant magnetism preserved in ancient crust. Some of the oldest rocks on Mars in the southern highlands carry magnetization patterns that can only be explained if Mars once had a global magnetic dynamo driven by a convecting liquid iron core. That dynamo is long gone, but the rock that solidified while the field existed preserves a record. We infer vanished oceans from valley networks and mineral deposits that only form in the presence of liquid water. We infer ancient impacts from basins, even when the impactors are long gone. The method of inferring absent objects from their present consequences is a normal and valid part of planetary science. The question is always whether the surviving evidence is specific enough to isolate one particular absent cause from competing explanations. That is the burden Nerio carries through the rest of the investigation. The name can make the idea vivid, the physics can make it respectable, but the science has to stay clear-eyed. If Tharsis loading, ancient impacts, and mantle dynamics together account for every measurable part of the signal without invoking a moon, Nerio is unnecessary. If a residual remains after those known processes are accounted for carefully, and if that residual has the right direction and amplitude, then the idea becomes worth pursuing more seriously. So every time we use the name Nerio from here, it carries conditions with it. Proposed, modeled, conditional. We are not talking about a discovered object. We are talking about a candidate explanation for one measured feature of Mars. And before a conditional explanation earns any real ground, it has to pass the loudest counter-argument Mars offers. If there is one geological feature on Mars that immediately challenges every elegant new hypothesis about the planet's shape, it is Tharsis. The rise is enormous, roughly 5,000 kilometers across, rising several kilometers above the surrounding terrain, home to some of the largest volcanoes in the solar system. Olympus Mons reaches roughly 22 kilometers. 3 more volcanoes line the same volcanic spine. Tharsis is not a wrinkle, it is a planetary-scale mass concentration that reshapes everything around it. Now imagine setting a massive weight onto one side of a slowly deforming world. The crust beneath bends downward. The surrounding terrain rises slightly in compensation. The gravity field changes. Instruments passing overhead measure a pull toward the concentrated mass. The rotational balance of the entire planet shifts as the load alters where mass is distributed relative to the spin axis. This is not metaphor. This is exactly the physical loading problem that planetary geophysicists model when they study Mars's long-wavelength topography and gravity. The mass of the Tharsis province, accumulated over hundreds of millions of years of volcanic activity, is large enough to flex the lithosphere beneath it by kilometers and to alter the global distribution of the planet's mass, and the evidence linking Tharsis to the global figure is strong. Work going back several decades has demonstrated that Tharsis loading explains a large fraction of Mars's long-wavelength gravity field and a significant part of the global topography anomaly. Research by Roger Phillips and colleagues published in Science in 2001 built a direct argument that Tharsis loading accounts for much of the planet's low-degree shape and gravity. Their analysis showed that when you model the volcanic load of Tharsis and the lithospheric response to that load, you can reproduce key features of Mars's long-wavelength gravity field. That is not a fringe idea, it is one of the most robust observational results in Mars geophysics. So the first major objection we encounter to a fossil-tied explanation is simple and direct. If Tharsis already explains a large share of the low-degree figure, how much room is left for a missing moon? If the dominant visible load already accounts for most of the long-wavelength gravity signal, the residual that Nerio is supposed to explain may be small, uncertain, or zero, but the construction of Tharsis has its own history, and that history adds complexity to the problem. Tharsis did not appear in one geological moment. The main phase of construction appears to have occurred primarily during the Noachian period, roughly 4.1 to 3.7 billion years ago. But volcanic activity associated with Tharsis continued through the Hesperian, the period from roughly 3.7 to 3.0 billion years ago, and isolated eruptions may have continued even into the most recent geological era of Mars. So the load that Tharsis applied to the global figure grew gradually over a long time. Any early fossil-tied signal was being added to a planet that was simultaneously accumulating Tharsis mass and adjusting to it. The sheer scale of the Tharsis mass gives some intuition for why it dominates the gravity discussion. Estimates put the mass of the Tharsis province at roughly 3 times 10 to the 20th power kilograms. Mars's total mass is about 6.4 times 10 to the 23rd power kilograms. So Tharsis represents something like 1 part in 2,000 of Mars's total mass, concentrated in a single region of the planet's surface. That may sound small as a fraction, but the concentration is enormous. Compare it to the way even a small weight attached to the rim of a spinning disk can visibly wobble the whole disk. Tharsis is not a small weight on the Martian rim. It is a geologically exceptional one. Its contribution to the low-degree gravity terms is correspondingly large, and disentangling it from any smaller amplitude signal beneath requires very precise modeling of its mass distribution and the lithospheric response. And the story gets harder when we add true polar wander. A large load on a rotating planet naturally tends to migrate toward the equator because that is where rotational stability is greatest. If a load grows gradually over a long period, the entire solid body can slowly reorient relative to the spin axis in response. Think of a spinning gyroscope. If you add weight to one side, the gyroscope does not stop spinning, but its axis slowly precesses in a way that adjusts to the new mass distribution. For a planet, the equivalent process shifts the solid shell relative to the rotation axis over geological time in a phenomenon called true polar wander. Mars may have done exactly this. The growth of Tharsis over its long construction history may have caused the whole planet to shift its orientation by tens of degrees, rotating the surface and everything recorded on it relative to the present spin axis. Work by Booley and colleagues published in Nature in 2016 developed a case that Tharsis loading can explain a significant reorientation of Mars on the order of 20 to 25 degrees. If that reorientation happened, then the geographic positions of ancient features relative to the present-day coordinate system are not what they appear to be. A fossil tidal signal impressed into early Mars, when the planet's pole was oriented differently, would now point in a different direction relative to today's reference frame. Think about what that does to the fossil tide argument. A fossil tidal signal would have been impressed into early Mars when the planet's rotational axis was oriented differently from today. The orientation of that early signal relative to the present-day coordinate frame is not something we can read off a map. It has to be reconstructed by modeling the history of polar wander. And every layer of correction adds uncertainty. Here is the distinction we need to hold on to. Tharsis is the dominant visible load, but the Nerio model is not claiming the whole figure. It is claiming a directional residual after the dominant contributions are handled. The key question is not whether Tharsis matters. It matters enormously and obviously. The question is whether Tharsis loading together with its polar wander consequences and the hemispheric dichotomy fully removes every significant directional signal from the low-degree gravity field, or whether something meaningful remains. And the polar wander correction deserves a concrete moment of attention. Booley and colleagues, in their 2016 work, proposed that Mars reoriented by roughly 20 to 25 degrees relative to its present spin axis as Tharsis loaded the planet. That means a feature that today sits at a particular latitude and longitude was, before Tharsis finished building, at a different latitude and longitude relative to the planet's rotational axis. For the fossil tide argument, this matters because the direction from Mars's center to the synchronous orbit is defined relative to the planet's equatorial plane. If Mars's pole was pointing in a different direction when Nerio raised its tide, then the direction the fossil tide would point today, after the planet reoriented, is shifted from where you might naively expect. Any calculation of whether the measured C22 residual points in the direction a synchronous moon would have left must account for this shift. And the magnitude of the shift depends on the polar wander reconstruction, which itself carries uncertainty. The correction is not impossible, but it adds a layer of model dependence to the geometry test. That is why the lost moon hypothesis is really a residual case. If all those combined contributions reproduce the measured low-degree field completely, Nerio has no place to stand. If after all those contributions are modeled as carefully as possible, a directional residual persists and points in the right direction, the hypothesis gets breathing room. So what we find is that the scientific burden on the lost moon model is heavier than it first appears. The model has to do more than observe that Mars is asymmetric and offer a synchronous moon as the explanation. It has to show that after the known Tharsis load and its consequences are taken seriously and accounted for carefully, a directional signal remains that points to a different origin. And Tharsis is not even the oldest answer available. Mars may carry an even deeper scar from something that arrived before any volcano rose. The northern lowlands of Mars are lower, smoother, and geologically distinct from the southern highlands. The southern hemisphere preserves older, more heavily cratered terrain and thicker crust. Looking at a global topographic map of Mars, the hemispheric contrast is one of the most striking features on any rocky planet in the solar system. But the giant impact explanation changed how we think about that contrast. Instead of treating the hemispheric dichotomy as a slow accumulation from many small, unrelated causes, impact models asked a direct question: could one enormous collision have produced the crustal and topographic contrast we observe? The answer from several influential studies was yes, at least plausibly. A very large oblique impact in the early solar system could excavate a basin corresponding roughly to the northern lowlands, redistribute crustal material, thin the crust across a hemisphere-scale area, and produce the north-south contrast in terrain age and crustal thickness. Think about the scale involved. The proposed Borealis Basin underlies the northern lowlands. It would be roughly 10,600 kilometers long and 8,500 kilometers wide, covering nearly 40% of Mars's total surface area. To feel that, consider that the entire Atlantic Ocean is roughly 9,600 kilometers wide. The proposed Borealis Basin is larger. It would dwarf the Moon's near-side hemisphere. It would be the largest confirmed impact basin in the solar system if the evidence holds up. The impactor capable of creating such a basin would be comparable in scale to the largest bodies circulating through the early inner solar system. The same era when Earth was still accumulating its final mass, and when the Moon-forming impact may have occurred. And the evidence for a giant impact origin for the dichotomy is not simply an argument from size. Work by Jeffrey Andrews Hanna and colleagues, published in Nature in 2008, took a different approach. They mapped anomalies in Mars's gravity field and found that certain low-gravity features in the northern lowlands trace an elliptical pattern. When you follow those anomalies across the planet, they outline a shape consistent with the rim of a giant buried basin. The gravity anomaly corresponds to the thinner crust you would expect at the base of a very large impact structure. This is not a crater visible at the surface. Billions of years of volcanic infilling, sediment deposition, and geological reworking have buried the original basin floor deep beneath the northern plains. But the ghost of the crater shows up in the gravity field because the thin crust it left behind is still there. Companion work by Margarita Marinova and colleagues, published in the same journal that year, applied numerical impact simulations to show that large oblique impacts could produce the observed crustal and topographic contrasts under plausible early solar system conditions. These simulations are not simple bullet and target calculations. They model how the pressure wave from the impact propagates through the planet, how the excavated material is distributed, and how the surviving crust responds to the sudden removal of so much material on one side. An oblique impact at the right angle sends more of its excavated material in a preferred direction, creating an asymmetric ejector pattern and an asymmetric crater rim. The geometry of the proposed Borealis Basin, which is more elliptical than circular, is broadly consistent with an oblique rather than a head-on collision. The Andrews-Hanna et al. Method is worth spending a moment on because it illustrates how scientists find things that cannot be seen. A crater the size of Borealis would have been progressively filled in by volcanic lava flows, sediment deposition, and dust over billions of years. The original crater floor and rim are not visible in topographic data alone because the northern lowlands look like a broad plain that has been resurfaced many times. But the crust beneath that plain is still thin, and thin crust means lower density compared to the thick crust of the southern highlands. Lower density means slightly less gravitational pull on a spacecraft passing overhead. By mapping the subtle gravity anomaly that outlines the thin crust region, Andrews Hanna and colleagues found that its boundary follows an elliptical arc consistent with a giant impact basin rim. The gravity field was showing them the ghost of a crater they could not see at the surface. That is the same basic method that would be used to test any ancient large-scale gravitational signal in Mars's figure, including a fossil tide. What you cannot see on the surface, you can sometimes still read in the gravity. Now this matters enormously for the lost moon case. The hemispheric dichotomy gives Mars a powerful external explanation for one of its most obvious asymmetries. An explanation that does not require any missing moon. If a planet-scale impact already explains the north-south contrast in crust and terrain, pointing to the hemispheric dichotomy as evidence for Nerio is circular. The dichotomy already has a stronger explanation weighting, but here is where we have to keep the categories clean. The hemispheric dichotomy and the triaxial residual that Nerio targets are not the same problem. The dichotomy is primarily a north-south contrast in crustal thickness and surface age. Nerio targets a directional equatorial component in the long wavelength figure. Those overlap in the broad sense that both concern Mars's asymmetry. But they are not interchangeable pieces of evidence. Claiming that the dichotomy supports Nerio conflates two distinct problems, so the impact camp does not directly disprove the lost moon hypothesis. What it does is remove a large piece of the easy rhetorical ground. We cannot point to Mars being globally uneven and hand the entire observation to Nerio. The north-south scar already has a serious independent explanation, and the categories matter here in a specific way that is easy to blur. The hemispheric dichotomy involves primarily the J3 and low-degree odd harmonic terms in the gravity field, the north-south asymmetry terms. The Nerio model targets mainly the degree 2 order 2 terms, the C22 and S22 coefficients, which describe the equatorial directional asymmetry. Those are not the same coefficients. A giant impact that produces the hemispheric dichotomy contributes strongly to the north-south terms. A fossil tide from a synchronous moon would contribute more to the equatorial directional terms. That means these two explanations are not simply competing to explain the same number. They address partially overlapping but distinct features of the gravity field. A viewer who walks away thinking either the impact or the moon explains Mars's weirdness has missed the precision of the argument. Both could be true simultaneously if each addresses its own specific part of the gravity signature. The question for Nerio is whether anything remains specifically in the equatorial directional terms after Tharsis and all its consequences are handled, not whether the hemispheric dichotomy has been explained. And the story becomes richer when we ask what happens after such an enormous impact. A hemisphere-scale collision would not only excavate and redistribute crust, it would inject heat unevenly into the Martian interior. The impact side would receive a large thermal pulse, while the opposite hemisphere remained relatively cool. That asymmetric heating could alter the flow pattern of the mantle and set up internal asymmetries that persist long after the direct impact scar has been modified by volcanic infilling and erosion. One violent external event could set off a cascade of internal responses that amplify and extend the asymmetry over hundreds of millions of years. So an impact can create the initial hemispheric contrast and then trigger internal processes that extend it. Some of Mars's large-scale structure may come from one violent event. Some may come from the internal response to that event. Some may come from volcanic loading that followed. And if a fossil tide contribution from a synchronous moon exists on top of all that, it is entering an already crowded figure budget. We now have three major explanation families for Mars's large-scale shape problems: volcanic loading, giant impact, and the internal dynamics we are about to consider. None of them require a vanished synchronous moon. The lost moon hypothesis is not competing against each of these families separately. It is competing against their combined explanatory power after each one is taken as seriously as the evidence supports. And that sets up the quieter but important fourth explanation, the one that comes from inside the planet itself. Planets are not rigid sculptures that hold whatever shape they are given. As long as heat can flow out of a planet's interior, the material inside can slowly move and reorganize. Mars is smaller than Earth and cooled faster overall. But early Mars was still a thermally active world. Its interior carried enough heat to drive significant internal motion across a long period of the planet's early history. Now, Earth's surface is broken into large plates that move around, driven by convection in the mantle below. Where plates collide, mountains rise. Where they pull apart, ocean ridges form. This is plate tectonics, and it keeps Earth's surface constantly recycled and renewed. Mars has nothing equivalent. Mars has what planetary scientists call a stagnant lid. The outer shell of the planet is thick and effectively immobile, sitting on top of the mantle like the lid of a slow cooker, rather than a set of moving pieces. Material can flow below that lid, heat can escape through it, but the lid itself does not break into plates and carry geological history around the planet the way Earth's crust does. That difference matters for how the interior shapes the planet. On Earth, the mantle's convective motion expresses itself through moving plates and recycled crust. On Mars, the interior convection cannot express itself that way. Instead, the interior flow has to organize itself beneath the unmoving lid, and the pattern of that flow directly shapes the long-term structure of the planet above it. Mantle convection is the process by which hotter, more buoyant rock rises toward the surface while cooler, denser rock sinks. In a planetary mantle, this happens over millions to hundreds of millions of years, not human timescales. The rock behaves like an extremely slow fluid at the depths and temperatures involved. But the patterns of that flow can be surprisingly organized. One especially important idea for Mars is what researchers call degree 1 convection. Instead of many roughly balanced convection cells distributed around the mantle, the entire pattern can become dominated by one broad upwelling in one hemisphere and one broad downwelling in the other. Think of the mantle not as a pot of water with many small bubbles rising here and there, but as a single very large bubble on one side, driving a planetary scale circulation. One side of the planet becomes dynamically different from the other because the large-scale internal flow is organized asymmetrically. That kind of global internal organization can produce a hemispheric scale crustal and topographic contrast without any external impact. And that is a real theoretical possibility. Modeling work by Roberts and Zom, published in the Journal of Geophysical Research in 2006, showed that degree 1 mantle convection in early Mars could reproduce the general character of the hemispheric dichotomy under plausible assumptions about the planet's interior properties. A single large-scale internal flow pattern, with no need for an impactor or a distant moon, can drive the kind of broad asymmetry we observe. The result does not prove that degree 1 convection is what happened, but it establishes that a purely internal mechanism is physically capable of producing the dichotomy. But then consider the hybrid models. A giant impact could create the initial hemispheric asymmetry. That asymmetry could then seed or reinforce a degree 1 convection pattern in the mantle by providing an asymmetric boundary condition for the flow. The impact heats one hemisphere more than the other. That thermal asymmetry creates a preferred geometry for the mantle circulation. The resulting internal dynamics could then amplify and extend the dichotomy, influence volcanic loading and crustal thickness, and preserve the asymmetry long after the direct impact signature has been modified or buried. A 2018 study by Citrin and colleagues in Earth and Planetary Science Letters developed exactly this kind of coupled picture. Impact plus convection working together. In their model, the giant impact does not produce the full dichotomy by itself, and degree 1 convection does not produce it by itself. The two processes work in combination, the impact creating the initial condition and the convection amplifying it. The result is a Mars that is neither purely impact-dominated nor purely interior-dominated. Think about how much that complicates the fossil tide case. The low-degree gravity field of Mars is the sum of many contributions added over a long and complicated history. Rotation contributes. Tharsis contributes. The hemispheric dichotomy contributes. Interior density contrasts from the thermal evolution of the mantle contribute. The way the lithosphere flexes under all these loads contributes. True polar wander contributes. If a fossil tide contributes too, it must do so in a way that is not already fully absorbed by the combined explanatory power of everything else. And here is why the scientific version of the lost moon argument has to be modest. The best version of the hypothesis does not try to compete with the established explanation families as a master alternative. It tries to find a specific residual after those explanations are applied as carefully as possible. If mantle convection and impacts and Tharsis loading together exhaust the observed low-degree signal, there is no gap for a fossil tide to occupy. If they leave a well-defined directional remainder that points in the direction the fossil tide model predicts, the hypothesis has a precise place to make its case. And this is also why the public version of the story can mislead if it gets too neat. The neat story sounds like, Mars is strange because it lost a giant moon. The honest scientific picture sounds more like, Mars is strange for several overlapping reasons, most of them already well established, and a lost moon is one candidate for a leftover component of the figure that the established families may not fully account for. Mars's stagnant lid is itself worth understanding a little better here, because it is the reason these interior dynamics are so influential on the planetary figure. Earth has mobile plates, and mobile plates constantly recycle the crust. New crust forms at ocean ridges, and old crust sinks back into the mantle at subduction zones. That recycling means the long-term memory of Earth's crust is limited. Anomalies are overprinted. Old structures are destroyed. Mars, with its immobile outer shell, has no such recycling mechanism. The patterns of internal convection beneath a stagnant lid can persist and accumulate for hundreds of millions of years without being disrupted by surface plate motion. That means the degree 1 convection pattern, if it established itself early in Martian history, could have driven the hemispheric asymmetry for a very long time. The stagnant lid is one of the reasons Mars still carries such deep memory of its early interior organization. And now we need to consider what this means for the fossil tide case more precisely. The internal dynamics of a stagnant lid planet produce long wavelength gravity signals at the same low harmonic degrees where a fossil tide would appear. The problem of separating the contributions is even more difficult than separating Tharsis from the residual. Mantle convection leaves density contrasts deep in the interior, and those contrasts contribute to the low-degree gravity field in ways that are harder to model directly than a surface volcanic load. Any remaining unexplained signal in the equatorial directional terms has to survive scrutiny from Tharsis loading and polar wander, but also from the long-lived effects of deep mantle organization. So where does the interior camp leave us? We know Mars may remember its own early heat and its own early impact history as much as it remembers any vanished companion. We know the major asymmetries have strong competing explanations, and we know the lost moon case survives only if it can identify something specific that those explanations do not cover. That something is not a story about how strange Mars looks. It is a precise geometric claim. And that is where the investigation has to narrow. Here is where the story has to slow down and become more exact. The evidence for Nerio is not a moon. The evidence is a shape. The moon is one possible explanation for part of that shape. And before we can judge the explanation, we have to understand what shape we are actually talking about and how we measure it. When scientists discuss Mars's triaxiality in this context, they are not talking about its equatorial bulge in general. Every rotating planet has an equatorial bulge from its spin. Mars's rotation-driven bulge is well understood and well accounted for. What the Nerio model targets is a different component, a directional asymmetry in the equatorial plane that goes beyond the expected bulge. Think of the equatorial cross-section of Mars not as a perfect circle, but as a slight ellipse with its long axis pointing toward one particular longitude. That preferred direction in the equatorial plane, after the rotation effects are removed, is the specific quantity the model is trying to explain, and measuring that directional term is the work of spacecraft gravity science. The Mars Reconnaissance Orbiter and its predecessors have spent years in orbit around Mars, transmitting radio signals back to Earth. Scientists track the Doppler shift of those signals continuously. When the spacecraft speeds up as it passes over a region of higher mass, the frequency of its radio signal shifts slightly toward higher values. When it slows over a region of lower mass, the frequency shifts slightly lower. These Doppler shifts are extraordinarily precise. Scientists can measure a spacecraft's velocity to within fractions of a millimeter per second. By cataloging the pattern of speed changes over thousands of orbits at different orientations and altitudes, scientists build a complete map of the gravity field. The gravity field is then expressed as a sum of spherical harmonic terms. The degree 2, order 0 term is the J2 coefficient, describing the symmetric equatorial bulge from rotation. The degree 2, order 2 terms, called C22 and S22, describe the directional equatorial asymmetry. Those are the terms the Nerio model claims to partially explain. They have specific measured values and specific orientations on Mars. The fossil tide model predicts that after the contributions from Tharsis loading and the hemispheric dichotomy are subtracted, the residual direction should point toward where a synchronous moon would have been orbiting billions of years ago. Now, a synchronous moon would leave exactly that kind of directional expectation in the figure of a deformable planet. Because the moon holds roughly the same position relative to the surface, its tidal pull keeps working along one axis. The distortion accumulates in a direction. If that directional distortion is then frozen into the figure as the planet stiffens, the preserved signal should have an orientation that reflects where the synchronous moon was sitting. And here is why that directionality matters scientifically. Many processes can make a planet uneven in some general sense. Fewer processes make it uneven in a specific, predictable direction. Fewer still make it uneven in a direction that lines up with a particular orbital geometry after billions of years of geological change and rotational history have added their own contributions. A directional prediction is much harder to satisfy by chance than a general claim about asymmetry. So the geometry test is sharper than anything the first few chapters have asked. After the known contributions are modeled and their effects subtracted from the measured gravity field, is there a low-degree directional residual whose orientation, corrected for true polar wander, matches what a synchronous ancient moon in the right orbital position would have produced? That sounds like a well-defined question, but the execution is genuinely difficult. Tharsis itself contributes to the low-degree directional terms, the C22 and S22 coefficients. The hemispheric dichotomy contributes. The lithospheric response to those loads contributes. Rotational figure changes contribute. Separating one physical contribution from another in the measured gravity field requires building models for each process and subtracting them in sequence. Each subtraction introduces uncertainties from the model assumptions. Picture it this way: listening for one instrument in a very loud orchestra. The violin section is playing a specific motif. You can identify it only if you know what the drums, the brass, and the woodwinds are already doing. The fossil tide hypothesis says there is a motif in the Martian gravity field that the other instruments do not account for. But before you can hear the violin, you have to correctly characterize the entire rest of the orchestra, and the model inherits a direct constraint from the amplitude requirement. A moon that produces too small a tide cannot explain the measured residual even if the direction is right. A moon massive enough to produce the required signal must then survive the orbital constraints that come with that mass. Geometry cannot be separated from dynamics. The direction and the amplitude have to belong to a moon that could have physically existed in the required orbit for the required time. There is also a subtlety in the subtraction that deserves attention. The contribution of Tharsis to the C22 and S22 terms is not simply proportional to its visible mass. The lithospheric response to Tharsis loading also contributes. The elastic properties of the lithosphere determine how far the flexure from the load extends, and those elastic properties change over time as the planet cools and the lithosphere thickens. So subtracting Tharsis's contribution is not a single clean calculation, but a function of the loading history and the lithospheric history, both of which have to be reconstructed from indirect evidence. Think about what that means for the uncertainty in the residual. If the Tharsis contribution to the C22 coefficient is uncertain by even a modest percentage, that uncertainty translates directly into uncertainty in the residual. A small error in the Tharsis subtraction can produce a spurious residual that points nowhere physically meaningful, or it can suppress a real residual that was there all along. This is not a reason to dismiss the hypothesis. It is a reason to understand that the test requires the Tharsis model to be good, simply adequate. The precision of the geometry test scales with the precision of the competing model. Better Tharsis models mean a cleaner test. That is one reason why the hypothesis, though it makes a specific prediction today, will be evaluated more fairly as the input models improve. The directionality is ultimately the test that is hardest to satisfy accidentally. If you subtract all the known contributions from the gravity field and find that the residual is pointing in a direction that is entirely inconsistent with any plausible synchronous orbit geometry, the model fails. If the residual points in a direction that falls within the range predicted by the fossil tide model after polar wander corrections, the hypothesis survives this test. The challenge is doing the subtraction cleanly enough that the residual's direction is meaningful rather than an artifact of modeling choices, so we can say something with confidence at this point. The best version of the hypothesis is not, Mars is asymmetric, so a moon did it. The best version is, there may be a directional residual in the low-degree equatorial figure of Mars that points to a fossil tide after the known dominant contributions are properly removed, and after the true polar wander history is applied. That is a much narrower claim, and it is the only version worth taking seriously. Because once the case narrows to that, the orbit becomes the next gate that has to be passed. A moon large enough to matter gravitationally is also large enough to create problems. That is the central tension in the Nerio model. The stronger the ancient moon becomes as an explanation for the directional signal in Mars's figure, the harder the physics of that moon becomes to satisfy honestly. Start with the Roche limit. This is the distance inside which tidal forces from the planet become strong enough to tear apart an orbiting body that is held together only by its own gravity rather than by material strength. For Mars, the Roche limit for a fluid body sits at roughly 7,800 kilometers from the planet's center. A fluid body is one held together only by its own gravity rather than by material strength. The exact position depends on the assumed density of the orbiting body. The synchronous orbital distance for Mars is approximately 20,428 kilometers. That puts the synchronous zone comfortably outside the fluid Roche limit by more than a factor of 2. A synchronous moon of the right density could, in principle, orbit Mars without being immediately torn apart by tidal forces. But surviving the Roche limit is only the first requirement. A synchronous orbit is not a safe permanent position. It is a balance point between the tidal forces from the planet and the gravitational forces from the Sun and other bodies. In an ideal two-body problem with no other perturbations, a synchronous orbit can be stable indefinitely. In the real early solar system, perturbations are unavoidable. The Sun's gravity continuously acts on the orbiting Moon and can shift the orbit over time. The process by which the Sun does this is called a secular perturbation. It does not push the Moon strongly on any single orbit. It applies a tiny systematic displacement over many orbits, very slowly accumulating, over millions to tens of millions of years. The cumulative effect of the Sun's gravitational pull on a synchronous Martian moon becomes significant. The perfect synchrony starts to break down. Now look at what the model actually requires from this orbit. The Moon has to form or arrive in or near the synchronous zone early in Mars's history. It has to remain close enough to synchrony for long enough that the tidal deformation accumulates and builds up in the planet's figure, it has to persist through Mars's high compliance window, the period when the young lithosphere is still thin enough and warm enough to record a strong signal. And then it has to leave the scene through inward migration, outward destabilization, or orbital breakup, in a way that is physically plausible, and the timing of all this cannot be arbitrary. Early Mars did not remain thermally soft forever. The window during which Mars's outer shell was thin and warm enough to allow a significant solid-body tidal response was finite. As the lithosphere thickened and the interior cooled, the effective compliance of the planet decreased. The Moon's residence time in the right orbital regime had to overlap with Mars's high compliance period. Too early, and the figure may not be preserved before the planet stiffens in a different configuration. Too late, and the planet may already be too cold and rigid for the deformation to matter. And the formation pathway for a synchronous moon is a question that sits before the survival question. Before a moon can maintain a synchronous orbit, it has to get there. The most natural route would be formation from a debris disk produced by an early large impact on Mars. Such a disk, if it formed early enough, could have produced moons at various orbital distances. A moon forming or migrating to near the synchronous zone would naturally become tidally locked in its rotation and could maintain a stable synchronous orbit for a period. Alternatively, a moon could have been delivered to near synchrony through tidal evolution from an initially closer orbit, but this requires specific angular momentum conditions and timing. A third possibility is that tidal evolution from a captured body could bring it towards synchrony, but as discussed, capture itself requires very specific conditions. Each formation route imposes its own constraints that have to be checked for consistency with the full scenario. Here is where the mass of the moon becomes a double-edged tool. A more massive moon raises a stronger tide on the planet below. Greater tidal force means a larger potential deformation and a better chance of explaining the measured directional residual. But a more massive moon also exchanges angular momentum and orbital energy more rapidly with the planet through tidal interaction. That can accelerate the evolution of the moon's orbit and shorten the very residence time the model depends on. The moon has to be massive enough to explain the signal, and not so dynamically energetic that it rushes through the required orbital geometry faster than the deformation can be built and locked in. Then there is the disappearance problem, which cannot be treated as a narrative handwave. If Nerio migrated inward toward the Roche limit, it would eventually be torn apart by tidal forces and dispersed into a ring of debris. Some of that material would gradually spiral down onto Mars. Some might reaccrete into smaller moonlets that eventually also fall. A large body disrupted near Mars would produce a period of elevated impact rates on the Martian surface as debris rained down. That could leave signatures in the distribution of impact craters or in the structure of the early Martian regolith. The ring scenario deserves particular attention because a ring of debris around Mars could itself have a gravitational effect on the planet's figure. A broad ring concentrated near the equatorial plane would add mass symmetrically in the equatorial region, contributing to the J2 term rather than the directional C22 and S22 terms. That would mean the disruption of the Moon does not simply erase the fossil tide it created. It adds a new signal in a different harmonic degree. Over geological time, as the ring debris falls onto Mars or disperses, that signal would change and eventually diminish. But during the ring phase, the planet's gravity field would preserve several overlapping signals. The fossil tide would still be there. The ring would be adding new equatorial mass. Infalling debris would be adding more. Separating those contributions billions of years later is a formidable modeling problem. The hypothesis does not fail because of this complexity, but it does inherit it. If Nerio migrated outward through some perturbation mechanism, it would eventually reach orbital configurations that are no longer stable, and the trajectory still has to be physically coherent. The solar tides mechanism proposed in the Efraimsky model provides a destabilization pathway. The Sun's gravitational pull gradually walks the Moon away from the synchronous balance, shifting the orbit in ways that then trigger faster ordinary tidal evolution. This is a plausible route to eventual loss. Think about what the absence of a single, unmistakable disruption signature means. Mars has had billions of years to erase, bury, and overprint evidence. A disruption event 4 billion years ago would have been followed by 4 billion years of volcanic resurfacing in some areas, impact gardening everywhere, and erosion in wetter early periods. The absence of obvious direct evidence for a disruption event does not automatically kill the idea, but the loss mechanism has to have a path that does not create contradictions we can rule out from the current evidence. And it is worth noting what the solar tide destabilization mechanism is and is not claiming. It is not claiming that the Sun physically dragged Nerio away from Mars. The Sun's role is subtler than that. A synchronous orbit is balanced between the outward influence of the Sun's gravity, the planet's rotation, and the tidal locking with the planet. If any of those conditions changes, the synchronous balance shifts. As Mars cooled and its rotational rate slowed slightly over geological time, the synchronous distance changed. The orbit that was synchronous at one epoch would not be exactly synchronous later. The Moon would find itself slightly outside or inside the exact synchronous radius, and ordinary tidal evolution would then take over and push it systematically in one direction. The solar tide accelerates this process by adding a periodic perturbation to the orbit that the synchronous locking cannot fully resist over millions of years. The model is proposing a real physical process, not a hand wave. But like every element of the Nerio story, it is a process that requires specific conditions to operate on the required timescale. The model has to be checked against those conditions before the orbital side of the argument is considered satisfactory. So this is where we stand with the orbital side of the problem. Nerio is not dynamically impossible. The synchronous zone exists at a safe distance from the Roche limit. Solar perturbations provide a plausible eventual destabilization pathway. Every one of these steps can be modeled, but together they create an accounting problem. The orbital case is not free. Every unit of mass that the Moon needs to explain the geometric signal costs something in dynamical plausibility. Every unit of dynamical plausibility gained by making the mass smaller costs something in the strength of the tidal signal. We have the mechanism, we have the geometric prediction, we have the orbital constraints. What we have not yet asked is whether the two moons Mars still carries can say anything useful about the one that may have vanished. So the clearest path toward understanding where Mars's present moons came from is no longer another distant spectrum or another indirect orbital estimate. It is a sample in a laboratory. That is why the JAXA Martian Moons Exploration Mission, known as MMX, is relevant to this investigation. MMX is designed to visit Phobos directly, deploy a lander briefly onto the surface, collect material from the regolith from a depth of at least 2 centimeters, and return that sample to Earth. The mission launched in 2024 and is expected to reach the Mars system in 2025, with sample return planned around 2028. Once a sample from Phobos is in a terrestrial laboratory, the level of possible analysis changes completely. Scientists can measure isotopic ratios with extreme precision using mass spectrometry. They can examine individual mineral grains under a microscope. They can test whether the material resembles Martian crust or mantle, primitive carbonaceous asteroids, or some combination of both. Now, oxygen isotopes are one of the most powerful discriminators. Different bodies in the solar system formed from material with slightly different mixtures of oxygen isotope ratios, because the composition of the solar nebula varied at different distances from the young Sun. Earth and the Moon share a very similar oxygen isotope ratio because they formed from material in the same region of the solar system. Mars has a measurably different oxygen isotope signature from Earth. A Phobos sample with a Martian oxygen isotope signature would strongly suggest the Moon formed from Mars-derived material, consistent with an impact disk origin. A sample with an oxygen isotope ratio matching outer asteroid belt objects would support a capture origin. Chromium isotopes provide an additional independent check, but before MMX returns its sample, the InSight mission has already provided new constraints on Mars's interior that bear on the fossil tide problem. InSight landed on Mars in November 2018 and operated until December 2022, recording seismic waves from Marsquakes and measuring the subtle wobble of Mars's rotation. The seismometer detected more than 1,300 Marsquakes over the course of the mission and used the travel times of seismic waves to determine the structure of Mars's interior. And one of the most significant InSight results was the size of Mars's core. Before InSight, models predicted a core radius of roughly 1,600 kilometers. InSight's seismic data revealed a core radius of approximately 1,800 kilometers, significantly larger than expected. To have that radius while still matching Mars's overall density, the core must contain a higher proportion of light elements than iron and nickel alone could explain. Hydrogen, oxygen, carbon and sulfur are candidates. This larger, more compositionally complex core has implications for how Mars evolved thermally. A core with more light elements has different melting behavior and convection properties, which affects how long a Martian magnetic dynamo could have operated, and how the mantle responded to the planet's cooling history. InSight also found that the crust at its landing site in Elysium Planitia is roughly 20 to 40 kilometers thick, at the thinner end of pre-mission estimates. The uppermost mantle appears relatively cold and rigid, consistent with a planet that largely finished its major thermal evolution billions of years ago. These seismic constraints are being used by planetary scientists to build better models of how Mars's interior was structured in the Noachian, the very period when Nerio would have needed to raise its tide. If the early mantle was hot enough and the early lithosphere was thin enough, the K2 love number for early Mars could have been substantially higher than its present value of 0.17, making tidal deformation much more significant. If the early Mars was already quite rigid, the fossil tide opportunity was narrower. InSight's data is helping to narrow the range of plausible early Mars interior states, which feeds directly into how seriously to take the fossil tide preservation claim. Think about why interior structure matters for the fossil tide case. The love number and Q factor of early Mars, which govern how strongly a young planet responds to tidal forcing, depend on the interior structure. Better constraints on the core size, the mantle composition, and the lithospheric thickness at different points in history allow more precise estimates of how soft Mars was when Nerio would have needed to raise its tide. If the InSight-informed models suggest that Mars's high compliance period was very short, much shorter than the orbital residence time Nerio requires, the fossil tide hypothesis becomes harder to sustain. If the compliance window is compatible with the needed orbital history, the mechanism looks healthier. Now, the origin debate for the present moons is genuinely still open, even with all the remote observation we have done. Spectral measurements of Phobos and Deimos from a distance have suggested a resemblance to dark, primitive asteroids in broad terms, but the interpretation has remained contested. Space weathering from solar radiation and micrometeorite bombardment alters the uppermost surface layer in ways that can mask or mimic compositional features. Martian dust can contaminate readings. Grain size and texture affect how surfaces reflect light. Remote sensing can take us only so far. And beyond the composition question, Deimos's dynamics provide an additional constraint on satellite history. Deimos orbits outside the synchronous zone and is drifting outward, but estimates of how fast it is drifting suggest that at the rate tidal evolution would drive it, Deimos cannot have been in its current orbit for the full age of the solar system, unless those tidal forces were much weaker than expected. That suggests either the tidal dissipation in Mars is much lower than current models indicate, or the present Deimos orbit is relatively recent. Any complete model of Mars's satellite history has to account for Deimos's dynamics as well as Phobos's. But here is the boundary that has to stay clear in the investigation. A Phobos sample cannot directly prove Nerio. It cannot identify a synchronous primordial moon from 4 billion years ago. By any measurement it is likely to return. The mass, orbit, and timing of a hypothetical early synchronous moon are not encoded in the present-day mineral structure of Phobos in any way we could read off. What the sample can do is narrow the family of satellite history scenarios that remain physically plausible for Mars. The gravity field remains the main courtroom for the hypothesis. The moons are witnesses whose testimony may become clearer over time. The interior models from InSight are constraints on the mechanism, but the directional low-degree gravity term is the actual evidence that the fossil tide case has to explain. By this point, we have assembled all the major pieces. We know the mechanism, we know the geometric prediction, we know the dominant competing explanations, we know the orbital demands, and we know what the present moons and interior data can and cannot tell us. The question now is whether the case for the hypothesis is stronger than the case against it. Now we can lay out the case for Nerio, and it begins with something real. Mars carries a directional feature in its long wavelength figure that invites explanation. Not every part of the planet's large-scale gravitational structure is fully accounted for by the obvious known processes. There is room for a residual question, and the Nerio model addresses that room with a physical mechanism rather than a vague appeal to mystery. Now add the mechanism itself. A young rocky planet can be deformed tidally. If the outer shell stiffens while that deformation exists, part of the pattern can be preserved as a fossil signal. This is sound physics. It does not depend on exotic principles. It depends on timing, mass, and orbital geometry aligning within the right early thermal history. Demanding, but not exotic. Then add the geometry. A synchronous moon makes a directional prediction about the preserved signal's orientation. That prediction is specific enough to test. It says not just that Mars should carry a residual asymmetry, but that the asymmetry should point in a direction consistent with a particular ancient orbital geometry. A directional prediction is harder to satisfy accidentally than a general appeal to asymmetry. If the residual points where the model says it should, after proper polar wander correction, that is a meaningful constraint. Think about what makes a directional prediction so powerful as a scientific test. The measured triaxiality of Mars has a specific orientation, pointing toward a particular longitude. If you were to guess randomly where a fossil tide might point, you would have a large range of possible directions. The model does not say Mars is slightly elongated. It says the elongation should point in a specific direction, consistent with a synchronous orbit at a specific longitude. That is a much harder prediction to satisfy by coincidence. It is the difference between predicting that it will rain tomorrow somewhere in the world and predicting it will rain in a specific city at a specific time. The more specific the prediction, the more informative it is when it succeeds or fails, and there is a broader backdrop to draw on. The general idea of inferring an absent object from its effects on surviving evidence is one of the most successful methods in the history of planetary science. Neptune was discovered this way through the perturbations it produced in Uranus's orbit before any telescope ever found it. The ancient magnetic dynamo inside Mars is known only through the remnant magnetism locked into the oldest crustal rocks of the southern highlands. No one saw the dynamo. We see only its frozen echo in rock that solidified while the field still existed. We infer dark matter in galaxies from the way their rotation speeds fail to follow the predictions of gravity from the visible stars alone. None of these inferred objects was considered unreasonable simply because it was not directly seen. What determined whether the inference was credible was whether the observed evidence was specific enough to isolate that particular cause. The Mars dynamo case is especially worth dwelling on here because it is physically parallel to the fossil tide idea in a specific way. The dynamo stopped operating at least 3.7 billion years ago, possibly earlier. No instrument can detect the magnetic field it produced directly, because that field has long since disappeared. But the rocks that formed while the field existed, the ancient magnetized crust of the southern highlands, still carry the orientation of the field at the time they cooled below the Curie temperature and locked in their magnetic signature. We infer the dynamo from the rock record it left behind. The fossil tide, if it exists, is the same category of evidence, a surviving physical record of a long-gone process, identifiable not directly, but through the constraints it places on a precisely measured present-day quantity. The question in both cases is whether the surviving evidence is specific enough to rule out alternative explanations. That is the standard we need Nerio to meet, not observation, specificity. The question is whether the directional residual in Mars's equatorial figure is distinctive enough, after all known contributions are properly subtracted, to isolate a synchronous moon as the cause. Put the case against it beside all of this, and the caution becomes immediately obvious. Nerio has not been observed. The direct literature source is a new model and preprint, not a long-standing consensus built from multiple independent investigations. The hypothesis is narrower than a fully settled theory in every dimension, and the competing explanation families are powerful when considered together. Tharsis loading, carefully modeled, explains a large fraction of the low-degree figure. The hemispheric dichotomy has a serious giant impact explanation with independent numerical support. Mantle convection and hybrid impact plus convection models can generate broad asymmetry from within the planet without any orbiting companion. True polar wander, driven by the Tharsis load itself, complicates any directional prediction from an earlier era. These are not fringe ideas easily dismissed. They represent decades of careful planetary geophysics work backed by multiple measurement techniques and multiple research groups. The lost moon hypothesis does not get to compete against each of them separately in an empty room. It has to earn a place in what is left after all of them are applied carefully. And the hypothesis imposes its own demands that grow with its explanatory claims. The moon must be massive enough to explain the measured residual signal. It must occupy the synchronous zone during the right thermal window in Mars's history. It must persist long enough for the deformation to accumulate and be preserved. It must then be removed through a physically plausible route, and the resulting figure signal must survive the subtraction of all known contributions without collapsing into modeling uncertainty. Think about what the hypothesis looks like at its most credible version. It looks like a possible contributor to one specific component of Mars's ancient low-degree equatorial figure, not a replacement for any of the established explanation families, not a master key that makes Mars suddenly simple, a contributor, a candidate for a residual that may remain after the dominant processes are accounted for. That sounds modest, but modesty is precisely what makes the idea scientifically respectable rather than scientifically ambitious in a counterproductive direction. Overclaiming would make the idea weaker, not stronger. An idea that pretends to explain everything explains nothing testably. So what we can honestly say is this: the lost moon hypothesis is serious enough to test, physically coherent enough to deserve careful attention, and conditional enough that it should not be spoken of as if it were established history. The best current answer is not yes, and it is not no. The best current answer is that Mars may preserve a directional tidal memory of a vanished companion, but that claim remains under heavy pressure from stronger, older explanations, and the verdict awaits better modeling of the known contributions and better constraints on the residual. So what do we do with a hypothesis in that state? It has not been falsified. It has not been confirmed. It makes a specific testable prediction. The competing models have not been fully exhausted. In that situation, the scientific response is to keep the hypothesis open, continue refining the competing models, look for additional constraints from new data. Resist premature closure in either direction. Premature closure in the direction of yes, Mars lost a moon is tempting because the story is evocative. Premature closure in the direction of no, Tharsis explains everything is tempting because the established explanations are powerful. Both kinds of premature closure cost scientific progress. The right response is precision. Clarify what the prediction actually is. Improve the models that the prediction must survive, and let the evidence decide. That is how hypotheses like this either earn their place in planetary science or are gracefully retired when the data runs out. And perhaps the most satisfying part of the whole story is not the question of whether Nerio was real. It is the method. Scientists are trying to judge an object that is gone by asking what it would have had to leave behind in the shape of a planet. That is a legitimate and rigorous way of doing planetary science, provided the surviving evidence is specific enough to isolate the cause. The final question is what evidence would make the case more or less specific. Picture what it would actually take to move Nerio from a conditional possibility to something more settled. Multiple independent lines of evidence would need to converge and point in the same direction. A single suggestive paper would not be enough. A headline announcing a lost moon would not be enough. What we need is a stack of independent constraints that all agree simultaneously. So the first test is better separation of the low-degree gravity contributions. Mars's gravity field is measured precisely. What remains difficult is assigning the correct fraction of the measured signal to each known physical process. Tharsis is large and well constrained in broad terms, but the detailed distribution of its mass and the lithospheric response to its loading still carry uncertainties. Better density constraints on the Tharsis volcanoes and better models of the elastic thickness of the lithosphere beneath them would tighten the Tharsis contribution to the C22 and S22 terms. If improved models of Tharsis loading, lithospheric flexure, and the hemispheric dichotomy leave a robust directional residual in the equatorial low-degree terms, that is the first condition. If that residual's orientation is also consistent with what a synchronous ancient moon in a plausible orbit would have produced, that would be significant progress for the hypothesis. Not proof, significant progress. Now, amplitude is the second line. The directional residual needs to have a magnitude consistent with what a physically plausible ancient moon could have produced during the available early Mars thermal window. If the residual requires a moon so massive that its orbital evolution becomes implausible within the constraints of the synchronous zone and the Rouche limit, the case weakens. If a moon within a credible mass range can produce the right signal during a realistic compliance window for young Mars, the case strengthens. And that window is the third line of evidence, Mars's interior history. Better interior models for early Mars, informed by the seismic constraints from InSight and future missions, can narrow the range of rheological properties the young planet plausibly had. The love number and Q factor as functions of Mars's temperature and compositional history determine how strongly and for how long the young planet could have responded to a synchronous moon's tidal pull. If improved models show that the high compliance period was very short, the mechanism becomes harder to sustain. If the compliance window is compatible with the needed orbital history, the mechanism looks healthier. Now, polar wander history is another gate. Improved reconstructions of Mars's rotational reorientation through the Noachian and Hesperian eras can tighten the correction needed to bring a fossil tide direction prediction into the present reference frame. If the corrected prediction continues to line up with the measured residual under better constrained polar wander models, the geometry test passes with more confidence. If the direction fails when the polar wander correction is refined, the geometric case collapses, and Phobos and Deimos samples from MMX form the fourth line. Not because they can directly confirm Nerio, but because they can narrow the family of satellite histories that are physically consistent with the Martian system. A strongly Martian impact disk origin for Phobos would make complex large-body satellite histories around Mars more credible as a class. A clear asteroid capture signature would suggest a simpler satellite history and reduce some of the indirect supporting context for Nerio-style scenarios. And there is a more specific constraint the Phobos sample could offer. If the sample shows evidence of a Martian impact disk origin, we can ask whether the impact that created the disk was large enough and occurred at the right time to have also set the conditions for a brief period of larger moon formation near synchrony. The timing of the impactor would be constrained by the age of the oldest material in the sample. If the Phobos parent disk formed in the late Noachian, the timing overlaps with when Nerio would have needed to be active. If it formed much later, the Noachian window for the fossil tide may have already closed. The MMX sample cannot identify Nerio, but it can set a chronological constraint that either opens or closes the timing argument. Look at what would seriously weaken the hypothesis. If better gravity field models, informed by improved Tharsis constraints and refined polar wander history, successfully reproduce the relevant equatorial directional terms without invoking any additional body, Nerio loses its explanatory foothold. Scientific ideas do not fail because they are challenged or because alternatives are attractive. They fail because the evidence no longer needs them. If the known processes fully close the residual, the hypothesis has no gap to occupy. That is not defeat. That is how science works. The competition between explanations is how models improve and how the surplus ones get retired cleanly. Think about what would weaken the case in a subtler way. If the mass and orbital requirements for a synchronous moon capable of producing the needed signal keep growing with each improved model, becoming increasingly implausible dynamically, the case weakens even if a directional residual persists. If the required formation pathway for such a moon within the early Martian system turns out to be dynamically rare or physically difficult, the hypothesis becomes a story that requires too many favorable conditions at once. A hypothesis is measured not only by whether its prediction matches the data, it is also measured by whether the object it requires is plausible in the universe we actually have. Now think about a concept geophysicists call model exhaustion. It describes the state you reach when a well-tested model accounts for every significant feature of the data within measurement uncertainty, leaving no meaningful residual. When a model is exhausted in this way, it does not mean all science is done. It means that particular data set has been explained, and the next scientific questions have to come from better data, from new observational windows, or from predictions about phenomena not yet measured. For the Nerio case, we reach model exhaustion when the established explanation families together fully account for all the C22 and S22 terms within measurement uncertainty. At that point, Nerio would have no remaining foothold in the data. Whether we have reached that point is genuinely unknown. Whether it can be reached with current models is equally unknown. Both outcomes are scientifically informative. A model that exhausts the data is as valuable as one that leaves a gap, because each tells us something precise about what the planet's history did and did not include. And there is also the question of future gravity field mapping. The current Mars gravity field models are already very precise, but a dedicated gravity mission with a lower orbit and longer coverage time could sharpen the constraints on the low-degree directional terms. Better separation between Tharsis's contribution and any remaining residual might be achievable with a sufficiently dedicated set of gravity measurements. Whether such a mission is on any near-term planning horizon is a different question, but the principle is clear. The gravity field is the courtroom, and better data from that courtroom can change the verdict. But that lesson goes beyond Mars. Planetary history is not written only in rocks and impact craters. It can be written in orbits, in gravity fields, in the long wavelength shapes of planetary bodies, and in the absences that those shapes force us to explain. Inferring an absent object from surviving physical evidence is a legitimate method when the evidence is specific enough to isolate one cause. The question we need to answer is always whether the specificity is there. That question, stated clearly, is the entire investigation. Not whether Mars looks strange. Not whether the lost moon story is evocative, but whether the residual signal is distinctive enough, after all known contributions are honestly applied, to require a cause that nothing still orbiting Mars can explain. Mars may have lost a moon, but the deeper truth is that Mars is still making us ask what a planet can remember about its own violent beginning. Mars is familiar enough to trick us. We know its deserts, we know its dust storms, we know the names of the rovers and landers that have crossed its surface. We know that its sky is a pale butterscotch at midday and deep blue near the horizon at sunset. 2 small moons orbit overhead. The familiarity makes the deeper strangeness easy to miss, but underneath the familiar surface, the planet does not fully balance. One hemisphere sits lower than the other. One side carries an extraordinary volcanic province that reshapes the global gravity field. The long wavelength figure of the planet preserves a directional asymmetry in the equatorial plane that still demands careful accounting. Mars is not a dramatic surface. It is a world whose whole body still carries the record of a violent and unsettled beginning. The Lost Moon model offers one possible answer to a specific part of that record. A large synchronous moon in early Martian history could, in principle, have raised a solid body tide in the young planet. If Mars stiffened while that distortion still mattered, the planet may have frozen part of that directional geometry into its own figure. Later, the moon left the scene through orbital evolution, instability, or disruption. The mark, if it was there, remained. That mechanism is real. It is physics, not mythology. The prediction is directional and specific enough to test, and that is why the idea deserves serious attention. But the older explanations deserve their full weight too. Tharsis is enormous, and its effects on the gravity field are documented through decades of spacecraft data. The hemispheric dichotomy has a serious giant impact explanation with numerical modeling behind it. Mantle convection and hybrid models can organize asymmetry from within the planet's own thermal history. The lost moon hypothesis does not stand above these explanations. It stands after them, and only if a well-defined directional residual remains once all of them are applied carefully. So what can we honestly say? We know Mars is physically uneven in ways that are measured precisely and not fully trivial to explain. We know a vanished moon could leave a fossil mark if it acted during the right thermal window. We know the present small moons do not confirm the hypothesis, but do show that Martian satellite histories are complicated and unsettled. We know the decisive evidence will not come from a striking image or a dramatic announcement. It will come, quietly, from whether improved models of Tharsis and the interior leave a directional residual in Mars's gravity field that keeps pointing toward a specific ancient geometry. What we do not know is whether that residual really belongs to a moon. Nerio remains possible. It remains conditional. And it remains exactly the kind of hypothesis that science should keep close enough to test and far enough from certainty to resist converting into a settled story before the evidence is ready. There is something fitting about that. The most important moon in Mars's story may be the one that is gone. We will know more when the gravity field tells us whether it left a forwarding address written into the shape of the planet itself. If you find yourself drawn to questions about what planets remember from their own violent beginnings, the story of Phobos and Deimos heads in a different direction. JAXA's sample return mission will eventually put Phobos material in a laboratory, and what that material says about where the small moons came from may narrow the range of histories Mars's satellite environment can have held. That investigation runs alongside this one. The evidence builds in parallel,